So here's what we're going to do now. We're going to tick off each of these final things. So we're starting today from, if I get my highlighter out, we're starting from number 12, defining current. Now we're going to go down through up to 18. And then as we previously discussed, we're getting rid of resistance. You don't need to worry about it. After that, we do need to talk a bit about electrical safety as well. So we will go from 23 down to 26. Obviously, this is a short lesson today, given the short recess. So what we're going to do, I don't know why that keeps popping up, sorry, is we're going to go through each of these and try and define them and go really quickly. So to start us off, what is current? Can anyone tell me what current is? Yes?
Your rate of flow of charge.
Great, okay. So our current here is the rate of flow of charge. Now, charge here, can anyone give me an example? What do I mean by charge? What's the most common thing that we speak about? Yes?
Electrons.
Tick. Okay, so e.g. our electrons. Now, when we're talking about charge, it has a very particular unit. Okay? Does anyone know what the unit is for charge?
Is it the same as current?
Oh, sorry, the unit for current, yes.
Oh,
Yeah.
And
Amplitude is a way of measuring current. Amperes? Yeah. Okay. When we're looking, oh, sorry, yes, what am I thinking? I was thinking, no, I'm getting confused here. I was thinking, wait, frequency for some reason was stuck in my head and I was about to say hertz. So good pickup, yes. So the rate of flow of charge is our, oh, and now the iPad's completely broken. It's all going well today. Amperes, great, and capital A, very good. Okay, done better than me anyway. So as we jump down, okay, that's 13. Define what current is, state the unit of current flow, tick. Now, I've had a few questions about conventional current flow versus electron flow, and here we're asked to describe conventional current. So before we do that, what I'm going to do is just over on the right-hand side, I'll make a mark and we'll go right over. I'm going to draw a really simple circuit. So what have I just drawn here? Battery, excellent. And this battery, it runs out and it goes through a light globe, comes all the way down. I've got a really simple switch here and then up and back into the battery. So if I was to ask you right now about electron flow, which direction would electrons flow in? So let me draw some pieces on here. Yep.
Are you talking about normally or conventional?
I'm talking electron flow. So this is what really happens.
They go from negative to positive?
Great. So in electron flow, we go from the negative and we head towards the positive. So in this case, I could draw some arrows on the inside showing that my electrons flow like this. So electron flow is from negative to positive. Now if I switch my colour of pen and let's go with majestic stars, okay? If I'm looking at majestic stars, okay, we do the opposite. And this is what I would call conventional, okay, this pen is actually the worst thing in the world. Never mind, I'm never doing this again. Conventional current, and this time we go the opposite direction. So I'm going to draw on the outside and I'll draw like this one. And instead my arrows are going the opposite way. So with conventional current, it's going from positive towards the negative. Question?
But is it like we just consider it to do that, or like it actually goes from positive to negative?
Great question. Electron flow is what actually happens. Okay. Conventional current is made up. Why? Because back when electricity was first being discovered, people thought, like, if I have lots of something, so the example that we commonly use is, imagine I've got a jug of water, okay? And with my jug of water, if I pour some of the water out into a cup, I would have had more here, so a positive amount, and then as I lose some of it, it heads towards this one here where there was less. And so people thought it goes from more to less. However, when we got a little bit more advanced with the technology that we could use, we actually realized that it was the negative things, these electrons, which were doing the moving. So why we have this idea of conventional current actually comes from before we properly understood electricity. So if you're asked to ever describe electron flow, you would be, this is from the negative anode to the positive cathode, or just the negative terminal to the positive terminal. And if you're asked to describe conventional current, you would just do from positive to negative. Are there any questions with this pointer? Great. So now we've ticked off 12 and 13 already. You know what? I'll colour them in green as we do them. So describe the differences between alternating current and direct current. Question?
I had a question. With the alternating current, it said there was alternating polarity. What's polarity?
Polarity is just positive and negative. You know how we have like the North Pole and the South Pole? You could also say that with a magnet, for instance, a magnet has a positive and a negative. So let's talk about alternating current versus direct current. In alternating current, you know what? We'll start with direct current, okay? So this is was it 14, sorry? Yep, so point 14 with direct current. I want you to think of, you know how we've drawn our circuits previously, and we've kind of said it's like all of the electrons are packed in right next to one another and they go all the way around this entire circuit in these cables. Now, the electrons in direct current, they only flow in one direction. And if I pick on one electron, and let me pick on this blue electron that I'm colouring in my circuit now, this one electron has to go from here and it has to travel all the way down there. And it goes from the negative terminal towards the positive terminal. So I like to make the analogy of this is like in an athletics carnival, this is like running the 400 meters. It goes around the track once, okay? And it's just one person doing all of the work. We happy with that one so far? If I jump now to alternating current, instead of just moving all the way forward, these electrons now move backwards and forwards. And the example that I like to make is the relay races from the athletics carnival. So hopefully you're familiar with the 100 meters, but we have 4 people running it, right? So the same distance is what I'm really trying to sell here. It's the same distance, but this time, instead of one electron doing the work, okay, we still have our forward progression here, but my first electron moves back and forth like this. My second electron moves back and forth like this. My third electron moves back and forth like this, and my fourth electron moves back and forth like this. How does it work? At some points, it's negative here and positive here. And then if I get a fresh colored pen, let's go with green, at some points it flips. And you're probably wondering, what is doing the flipping here? It is the battery. The battery, oh, that's an interesting looking wire. What the battery does, or what the voltage source does, is it flips its polarity. So what I mean by this, if I write battery flips / changes polarity, it means that the positive becomes negative and the negative becomes the positive. And they do this a few times each second, okay? And so it's not just once per second, it's happening multiple times per second. Now the benefit, what do you think the benefit of this one might be in terms of AC versus DC? Will 4 people run 100 meters faster than one person runs 400? There you go. So it's a bit better for us holding on to our voltage. Question?
Does this have anything to do with waves?
With waves, yes, if we go back to it and we dive into it, but not as far as we're going to ever talk about in the year 9 level. Question?
I'm really confused. So when you're talking about the part where there's just one that moves and then there's the multiple, are you talking about electrons?
Correct. Yes. So each of these arrows, if you like, the blue arrows that I've drawn on now, this represents my electron. and one electron does all the work in DC. Well, it's actually this electron, and then the next electron comes through behind it, so on. But in these ones, I have these electrons which kind of work together now to help carry that charge. Question?
Since alternating current is like faster, does that mean it's like that's the current that's used for like household electricity?
So alternating current is not technically faster, it's just better at carrying large quantities. So let's make the final point here with DC and AC. When I'm looking at DC, I'm going to switch to my different color pen again here. We'll go with purple, okay? My purple pen. DC is what you have coming out of your household power sockets. So even the ones that we can see around the room right now, so in Australia, they look like this. Coming out of these sockets, that is going to be 240 volts. That is DC. Now, we supply electricity from the power station. I couldn't even draw a power station if I tried, but box, there's a power station. Don't ask any questions about it. And what happens is there's lots and lots and lots and lots and lots of voltage there, okay? Let's say that there's 10,000 volts, okay? And at this power station, what we use instead is alternating current because there's less drop off, okay? The DC works in a short distance, but the alternating current works better over a longer distance, so we don't lose as much. And that's all you need to know. Just keep it really simple. Question?
Do certain things that plug into household power sockets require like more voltage?
No. So the maximum that we have coming out of our power sockets is 240. If you go to America, off the top of my head, they only have 120 volts coming out of the power socket. So in Australia, we actually have quite a high voltage. So if you ever go to America, I know my wife is a really, really big tea drinker. She hated it in America because they don't have kettles, because their power sockets aren't powerful enough to power a kettle. And so she had to boil water on the stove or heat it up in the microwave. They don't have kettles, okay? Well, they know what a kettle is, but it generally, it won't work as well. So they tend not to have them. So I'm moving on now. We've done 14. Are there any questions about alternating versus direct? Great. Measure current using an ammeter. I'm just going to write a single word. What do we need to do to make sure that this current can be measured using an ammeter? Do we insert it in series or in parallel? Series. Very good. So insert in series. That's all we need to know there. So 15, done. 16, apply conservation of charge principles to determine the current around a simple circuit. So these right now are our two current laws. So I'm going to write them off to the side here. We have our first current law for series and for parallel, right? So in both cases, we have the total current, so capital I, little t. In series, what is our current law? Does anyone remember? Yep.
I1 equals I2.
Great. So the current at all... Oh, sorry, I've messed that up. Oh, now I've broken it. That's a great question. I don't know why it does this from time to time.
Feel the iPad.
Yeah, I need to get a new iPad, I think. Equals I2 equals I3. And what about in a parallel circuit? Excellent. It's the opposite. So I1 plus I2 plus I3 dot, 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 dot. Okay. So this is for up the top, a series circuit. Two different colors, series and for parallel. So this is for applying our charge principles to current. So basically, what's the ammeter one? An ammeter measures current flow, and we insert an ammeter in series. That's all we need to know. Now for 16, we're using these two different rules to figure out how many amps, how much current is flowing around the circuit. Yeah, question?
Is that the conservation of charge?
well, conservation of charge is effectively just telling us that the total charge is the same throughout series circuits, and it's cumulative. It adds in parallel circuits.
Fair.
That's all it's saying.
Yeah.
Great. 16, done. Flying through it. Okay, so, oh, yep.
Isn't there another one?
For voltage, yes, but right now, the only thing that we're looking at is current in this one. Okay? Which brings me on to point 17. Apply voltage and current rules to determine voltage and current values around simple circuits. So let's instead focus now on the voltage ones, given that I've already got the current ones written up there. So, it is just, easy way for us, the opposite here. So if I go series and parallel, this time I'm doing VT, so total voltage. And when I have a look, if in a current, if we're measuring the current through a series circuit, you notice how everything is equal to one another. In this case, it can't be equal, they must be added to one another. So is equal to V1 plus V2, dot, 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 so on and so forth. And parallel, exactly right, you just switch them. So parallel V1 is equal to V2, dot, 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 so on and so forth. Okay? My advice is if you learn one, you can just use it to switch around. Because if you learn, say, the one I like to learn personally is series voltage. If I learn series voltage, I know that parallel can't be the same as that. I also know that it can't be the same as series current. And then I know that series current can't be the same as parallel current. And so I've now learned all four just by learning one equation. Okay? So when you get into your test, if I'm you, I'm probably writing down one of those rules on the front page while it's fresh in my mind, so then I'm not second guessing myself later in the test when I'm thinking, was it negative? Was it positive? Oh, not negative or positive, that's a completely different thing. Was it equal to one another? Was it added to one another? So on and so forth. So, 17, done. Look, you can go and practice those later. Okay, you've got plenty of practice examples. What we're going to do now is some explanation. So, let's think about voltage and current impacting the brightness of a bulb. And this comes back to our definitions of things. So over here, if I jump down a little bit, we've got 18. Okay. Let's think about voltage and how voltage is going to influence our key idea, which is brightness. So, number one, if I increase the voltage, what is going to happen to the brightness of a globe?
Increase.
Excellent. The brightness will increase. Maybe I'll just draw a line here like this. Okay. Secondly, and rather easily now, if I decrease the voltage or the push through a circuit, what's going to happen to the brightness of the globe? Decrease. Excellent. Now let's have a think about current as well. Okay. So if I have current, and I have brightness. If I increase the current going through a circuit, so increase capital I, what happens to the brightness throughout a circuit? Increase. And if I decrease the current flowing through a circuit, it will? Now this all sounds a little bit too good to be true, right? It's all very straightforward, it's all very easy. So let's add one more step to this. Okay, and it's probably beyond the scope of your pointers just a little bit, but explain how voltage and current impact the brightness of a bulb. I'm actually going to tie it into our voltage laws and our voltage rules. But before we do that, question.
Why did you do the I for brightness as well?
The I for brightness, oh sorry, that's a great point. I shouldn't have. Yeah, so if I'm talking voltage, okay, and I'll put a big squiggly line here, and I'm talking in series. If I increase the voltage in series, what happens to all of the light bulbs? Are all of them brighter, or is only one of them brighter? They're in series right now. Yeah, okay? All get brighter. Not the best terminology, but you know what I'm talking about. If I then jump to parallel, okay, when we look at a parallel circuit, if I increase the voltage going to one branch of that parallel circuit, only One globe gets better. What if I increase the voltage going to, or if I decrease the voltage going to one branch? It will decrease the brightness. So when we look at the voltage in parallel, and this comes back to our rule over here as well, VT equals V1 equals V2, okay? I need to make sure that when we're parallel, they will all get brighter. And the way to do that is all parallel branches receive the same voltage, thus the same brightness. Question?
How would you increase the voltage on one branch?
Exactly. Can you? What could you do instead, do you think, to make sure that one branch might have more of the voltage share? It would be more to do with series though, right? What could you do? We could increase the,
I was going to say add a switch.
add a switch, well, not quite, but what we'll do is we'll increase the resistance, because if I increase the resistance, it gets more of a voltage share. So this is really, to be honest with you, it's more to do with series. That's my apologies there. Now with current, this is the main one for us. When we talk about current and we talk about series circuits, okay? In series, what happens to the brightness of globes as we continue to add more globes? Great. So as I increase the resistance, what goes down? Good. Current goes down, and that is what causes the brightness to decrease. So if I increase resistance, I decrease the current, and that's also going to decrease the brightness. What about in parallel now? What happens in parallel? If we go back to our parallel laws, they're cumulative, right? So they add together. All of our branches add together. So what's going to happen in a parallel circuit with the brightness of globes and current? If there is less resistance, there will be greater current, and the brightness will go up. Now this, I want to note, depends on the branch. Okay. So for us, I'll be honest, this is your focus. What I've just highlighted in yellow there. That's where you should be really focusing. It's just important to still discuss series and parallel. Okay then.
So if both voltage and current increase, then so does the brightness.
Correct. Yeah. And generally speaking, if you increase the voltage, you're also increasing the current. Great. So if resistance stays the same, that is. Yes.
In the test, if the point 18 was in there, would it mention resistance at all? And would you have to?
No, because this pointer is focused purely on voltage and current. Yep. So we're skipping over 19 through 22. We're almost there. We've only got 4 more left to go, and then we're all done. So apply the conditions of current flow to electric shock. So how many conditions of current flow are there?
3.
Very good. Okay, so let's write down here 23. What are the 3 conditions of current flow? Oh, question first.
Was that not 17 and 18 that we just?
It was, and then we skipped resistance, and now we're up to 23. Okay, so with 23, what are our 3 conditions for current flow? We've done these previously. Let's chat about them. A load, very good. And what's the other word for a load? It's something that?
Uses.
Very good. Uses the electricity. What else?
Complete circuit.
Great. We need a complete circuit of what? Very good, everyone. Of conducting material. And what's the final thing that we need? Yeah?
A voltage source.
Very good. Can anyone else give me an example of a voltage? What am I right? Whoa. Sorry. I've got something else going through my head clearly. Voltage source. What's an example of a voltage source then? Yeah?
Battery.
Yeah, a battery, maybe one other one that we've used in class as well. Can anyone think of it?
The cells.
A cell? Yeah, a cell is like a unit of the battery. Yeah?
DC power supply.
Yeah, like a power pack that we've been using in class. Question?
What's a lollipop?
Yes. Yeah.
Right, is the voltage source the electromotive force?
The voltage source is the electromotive force, yes. So we could write here that that's the voltage at the voltage source, yes. So here's what we need to do for this pointer. This is already a separate pointer, right? Identifying these three things, but we're now asked to relate it to electrical safety. So in the case of you doing some electrical work at home, maybe you're helping mum, dad, someone at home out, in terms of the load, what would be the load if, say, you were doing some electrical work in a little bit of a dangerous environment? What could be the load? Yeah, okay. Us/you, okay. What about the voltage source? Where are we most likely to get zapped from at home? Excellent. It's most likely to come from a power point. Or you might remember the example of the man drilling into the roof. We've also got cabling in the roof, wires in the roof. Good. Now, if all of the electricity is coming from the power point, and for whatever reason you've decided to, touch the electrical power point with some metal, and it flows through you, it needs to complete the circuit. So what do you also need to be in contact with?
Ground.
Right, so you need to be grounded. Okay. If you're not in contact with the ground, will you get a shock?
No.
Can you levitate forever?
No.
No, you can't fight gravity, okay? So, yeah, if you jump and let go, if you're in the air when it's coming through, you will not get shocked. However, if you jump up, you're holding on to the power point and then your feet touch the ground, then the current flows through you instantly.
What if you're in a
If you let go, then you might have a potential difference. Your hair stands up on end, but then when you hit the ground, all of a sudden your hair falls down, similar to when we looked at the Van de Graaff generator. Okay. So that is that pointer there, 23. Apply the conditions of current flow to electrical shock. Is that every single version of it? No, but it's the easiest one for us to do now. Question?
if you're in a plane, you get electrocuted. Do you get electrocuted even though you're touching the ground, but it's not?
Oh, great question. I'm gonna have to think about that one. Wow, we're really taking this to the extremes now. I like it. Yes, question.
Are all electric shocks because of short circuiting?
No. We'll talk post-test about something known as static electricity. We can get electric shocks from static instead, which is just the build-up of difference. So yes, but not always. Yeah. Question?
So if you've got like a phone charger that's plugged in, but it's not plugged into your phone, do you get electric shock?
Yes, because it'll flow through the scissors into you. However, you've got plastic on the scissor handles, so that might insulate you from the shock.
Oh, is that why you have plastic on the scissor handles?
No, that's more so you don't hang on to the metal and chop your fingers off. Final question.
What's the shock when you like shock someone?
That is static electricity.
But how does that happen?
We'll talk about that after your test. We're doing 2 whole lessons on it. It's a lot of fun. I'm bringing the Van de Graaff generator in here, so we'll use it. Yeah. So, 24, state the factors affecting the severity of an electric shock. Now, for 24, I'll just do it down the bottom here to save us a little bit of time. 24, there are 3 main factors that we need to know about. This was from Miss Rogers' lesson earlier on last week. Does anyone remember what are the 3 factors, let me just pull the pointer up here so you can all see it, that affect the severity? Do you want to give me the first one?
Like the time spent.
Great, okay. So the word that we're going to use is the duration, okay, of exposure. So how long are you exposed to that voltage source? Do you want to give us the second one?
Halfway.
Great. Now, in terms of the pathway, I'm going to write good and give an example, and then I'm going to write bad and give an example. So what's a good pathway for us? Like,
You're
Not going the hard
Oh, thanks.
or mostly our skin, okay? If you damage your skin, oh no, you get a nasty burn, it's probably not the end of the world. The very, very bad, not so good ones though, would be your heart and your brain, okay? So we don't want electricity running through our heart, okay? Our heart relies on electricity in order to pump, okay?
So then why don't we put electricity in the heart?
Because if we send too much electricity through it, it will
So why don't we
fry it.
use
Defib is like a very high voltage shock to restart the heart. So there's a part of the heart called the sinoatrial node, and it can go out of rhythm or it can stop, and we're trying to zap it back into action. Question?
Oh, I was just going to say 3.
Oh, yes. Shh. Number 3, please.
The voltage, like the amount.
Good. Okay, so voltage slash current. Okay, so the one we really want to talk about, to be honest with you, is this one here. I'm going to highlight it. The 3 big ones. Okay, current. Okay, now what about the current? If it is high current, is it going to be bad for us? Yeah, so we want low current. Okay. Number 25, explain how short circuits are created and explain their dangers. So, can anyone tell me what is a short circuit? Yeah?
Oh, it's like a circuit without a load.
Good. Circuit without a load.
An accidental path of very low resistance that bypasses intended load.
Great. So, for this one, we're going to combine both of your responses. Okay? So, a short circuit, okay, is, I'll do a few dot points here to break it down, is an accidental pathway. Is lower resistance. Now, you mentioned at the start that could be due to less or fewer loads is what I should say. Let me get rid of less. And what else am I missing here?
Bypasses load, intended load.
Great. Bypasses, intended load slash route. Okay. So, in the case of a short circuit, why are they so dangerous? Let's think not about us forming a short circuit, but let's think maybe a short circuit forms at something at home. What are some of the potential consequences that could occur? Yeah? Good. Okay. So in terms of here's short circuit, let's chat very quickly about some consequences of a short circuit. It causes increased risk of fire, and that's because the electrons are flowing through the circuit and cause it to heat up, or, yep, kaboom, that's fine too. What are some other consequences? Yep.
It could like power out.
Mm-hmm. So it could lead to a, oh dear. So a power outage, okay, slash damage to property. I don't just mean properties in houses, I mean like the things that you own, right? Anything else? Maybe let's do our final one as us. What's the bad thing if we form a short circuit? Yep. Yep. Electrocution. Not fun. Not encouraged. Yep.
So how is the short circuit? How is the accidental pathway made?
How is the accidental pathway made? Lots of different variants here. So if I was to draw, say, a really basic circuit, and it's got a light globe and a battery, and then one day, all of a sudden, a few different things could happen. Maybe the cables fry and 2 cables that didn't touch each other previously do, and now I've just got an alternate route here. And so instead, my electrons just go like this. and it causes those wires to heat up and up and up and up and up. Maybe there's water that connects two wires that shouldn't be in contact, so on and so forth. Yeah.
Why? Oh, no.
Okay. Yep.
Why does it heat up?
Why does it heat up? Because what we've got now is lots and lots of energy, which is going the same way, the same time. So the easiest example to try and visualize it for yourself is like normally if you put your hands together and you rub them like so, back and forth, it heats up a little bit. And that's what happens with our wires, right? They heat up a little bit. But imagine now, because we've got all of this energy and there's no resistance, the flow, the rate that they're doing it has increased. And if you rub your hands together really, really quickly, they get really, really hot. The same thing is happening through our wires.
Oh.
Beg your pardon?
It's like when I have a campfire, like.
Campfires are good.
With the sticks and you go like this.
That's split, man.
Yeah.
No, you can do that with sticks as well, but you turn it. Anyway, we're getting distracted. Last pointer, and we're done. Okay, last pointer. Let's get it done. 26, define each of the following safety devices and describe their purpose and function. Okay, I'm not going to define them here because I'll give you slightly weird wording. And what I'd encourage you to, pardon me, instead is can you go to your book and just get the formal definition for me? But what we will do right now instead is we will chat about their purpose. Okay, so a fuse. Can anyone tell me what does a fuse do? What is a fuse designed to do?
It melts when there's excess.
Excellent. So it melts / breaks when what is too high? Great. When current, I'm going to shorthand here, when I is too high. Because it comes from the French intensity du courant. I can't pronounce French very well. So that's probably not even how you say it, but that's where it originally came from. A circuit breaker. Can anyone tell me what makes a circuit breaker a little bit different?
It can consider breaks.
Great. So, does not break. But what flips it off then? I'll get to your question in a second, but I want to relate these two things. If it doesn't break, how does a circuit breaker actually work? Yeah.
Is it the magnetic force?
Excellent. So when we have electricity, it's tied to this idea of electromagnetism. So it does not break as, oh no, it's randomly putting letters in again.
So does the circuit breaker?
So let me write it out for you. Does not break as current increases, so too does the magnetic field. And similar, you've all played with magnets at some point in your life and they can magically move things around, especially metallic objects. What happens here, as the magnetic field increases, so too does the magnetic field, which flips a switch, breaking the current. Now, can anyone tell me why do I not want them to break? Why do I want like a circuit breaker as opposed to fuses? Up the back, yep.
You have to, like, you have to get a new one after.
For which one?
The fuse.
Yeah, exactly right. So for a fuse, we need a new one every time. Circuit breaker, we can just go out the front to our meter box and we can flick them back on and we're all good. Question?
Is a circuit breaker and a safety switch the
We'll
same?
talk about that in just a second. Okay. What then is the purpose of an earth wire in terms of our safety? We spoke about a toaster when we did this example. What's an earth wire? Yeah?
Isn't it like radar?
Great. So it is I'm going to write it in purple just to make it clear because I'm running out of room here. Pathway for electricity to flow that isn't you. Okay, so when you touch your toaster, for instance, if you've got a nice metal toaster, it's got an earth wire in there. Why? So that the electricity will flow back out through your wall socket as opposed to through you. Okay? People wouldn't like toast very much if you got electrocuted every single time you went to make some. Yes, question?
So if you do put a
No, it will go to you. So
Did you get a
please, if you learn anything from this electricity unit, it is not to stick forks in toasters. Question.
How come my laptop charger doesn't have an air fryer? My laptop's made of metal.
But isn't the charger plastic?
Yeah, so it's insulated.
Wait, but
Insulated.
that's the thing, is plastic.
Some are, some aren't. Some toasters are metal.
But no, the plasticky stuff around the wire is plastic.
Yeah, but this is running into, so within the toaster, you know how we've got those things that heat up, the metal bits? The reason they heat up is we pass a lot of electricity through it so that they heat up. So that little part inside the toaster is actually electrified. If you now stick metal into toaster, you are now passing electric current through whatever you've stuck in there, plus that runs through you into ground, you die.
But the laptops get hot when you charge them.
Laptops can get hot, and that's a consequence of electrical energy accidentally getting transformed into heat energy, which is a normal transformation for every kind of reaction to make. Yeah. 26, final one, safety switch RCD. Safety switches and circuit breakers have a lot in common, okay? But the difference here is I want you to imagine our school right now would have a few circuit breakers out the front. And for us to trigger a circuit breaker, it's going to have to be a really, really big current going through. And it might take out electricity to the entire science block or the entire school. If, say for instance, someone magically decided to stick a fork into a toaster in a science classroom and it caused a short circuit in our room, do we want the power to the entire school going out? No. So what we've got are these things called safety switches. Let me use my blue pen here. And this is just a circuit breaker. I really shouldn't use the word circuit breaker to describe it, but it's almost identical, but it is local. So see our power points around the room. So if you're towards the lab benches, you can see them on the lab benches at the front. You can see them sticking out the wall. They've actually got these safety switches built in. So that if a switch is tripped, we can reset it locally as opposed to taking the entire power for the entire school out. Okay? Question?
So is it localized to the specific power?
Correct. Yes. Question?
Does only the safety switch detect a difference in current between the...
Correct.
Oh, okay.
Yes.
Is the power shut down with the key? Is that the safety switch?
I beg your pardon?
Is the power shut down with the key the safety switch?
Yeah, in the science classrooms we have additional ones because we have stuff that can go more wrong than, say, in HASS.
Wait, so you have to manually do it?
I can